All right, well, welcome everybody to our weekly Wednesday webinar series using simulation for the thermal management and fire protection of buildings. Real quick, if you need your continuing ed, check GoToWebinar. That will be emailed out to you an hour after the session. Check your spam, mark them as safe. A survey will be sent after the session, as well as it'll pop up in your email. Make sure to take that survey. We definitely appreciate your feedback, even if you don't need CEUs. Also, real quick, is the upcoming webinar events that we have. Next week, we'll be using battery buildings as a battery. And then we're trying something a little bit new, trying some different dates. So this is actually on a Tuesday, and we're going to be hosting at 2 o'clock Eastern, smart ventilation and smart duct systems. If you want to continue to get these sessions, get access to them without registering, want to support our mission, get discounts on paid courses that we're having coming up and discounts on green building certification, as well as much more, you can become a member today at our greenhomeinstitute.org, become a member on our website. Huge thanks to our first sponsor, Niagara Conservation. Did you know that toilets are the #1 users of water, and water bills are going up exponentially every day? And so what Niagara has is the Niagara Stealth, lowest flowing toilet on the planet, and it's a single flush system, none of that dual flush. It's also got an ADA approved side handle. So if you want to keep that normal side handle look or have it for accessibility needs. This is a WaterSense certified toilet. It's vacuum assisted, and it has glowing reviews from many affordable housing renovation specialists that we've worked with. On top of that, you can throw in the 0.5 shower aerator and the 1.25 shower head, and you're going to get super low flow technology. This session is also brought to you by Build Equinox, featuring the new Serve 2, a smart ventilation system. Unlike traditional ERVs or HRVs, it features many qualities of smarter balanced ventilation and feedback and monitoring. With the standard ERV or HRV, you get a constant low airflow rate with no relation to actual indoor air quality or occupancy. For the first 3 days, when the home is occupied, the air quality is poor. The ERV just can't keep up. But when the occupants leave on vacation, the ERV keeps ventilating and wasting energy. Since the Serve actually monitors air quality, it ventilates only when it's needed. Compared to an ERV, the Serve can ventilate up to 300 CFM, quickly purging pollutants from the home. With no ventilation as needed, the Serve can recirculate and unify the home, providing some additional heating, cooling, dehumidification in an energy efficient manner. The Serve does this by monitoring both CO2 and volatile organic compound levels to determine when ventilation is necessary. Many gases are undetectable to the human nose, yet you can cause significant impairment to health, cognition, and sleep quality. Instead of an ERV exchanger cord, the Serve uses high-efficiency heat pump to exchange energy between incoming supply and outgoing exhaust air. What does this mean? Conditioned, comfortable air unifies the home instead of dragging exterior rooms away from the comfort. Serve also features a standard 10 by 20 size MERV 13 unit. The Serve is manufactured right in Urbana, Illinois, 100% US-made, 100% solar-powered factory. It can also work well with heat pump water heaters, such as the Rheem Prestige, to boost capacity or work with Radiant. It can work very well on green building projects that we've seen to distribute Mitsubishi mini-split heat pump air around a home or multifamily unit, and can finally work really well with a geothermal system with a GeoBoost, such as the GeoComfort geothermal system. Check the Serve 2 out at buildequinox.com today. All right, well, welcome everybody to using simulation for the thermal management and fire protection of buildings. This course is approved for 1 hour in continuing education units, GBCI, AIBD, NARI Green, Certified Green Professional, BPI non-whole house. It's also approved for health, welfare, and safety through the American Institute of Architects, which may make it applicable to your state-based design or contractor license. Today, I'll be your moderator. My name's Brett Little, and I'm the executive director here at the nonprofit, the Green Home Institute. And anytime we're talking about modeling and simulation, we always say, why guess when you can know? We can start to know the performance of buildings before we start a project, so we eliminate the surprises and the guesswork, and that's why we're excited to be hosting Nicholas. He joined COMSOL France in 2004 and is currently the head of their development team. He is also the manager of the heat transfer module. He studied engineering at ENSI MAG before receiving his PhD in living modeling from Joseph Foyer University. All right, so with that, Nicholas, I welcome you, and I will turn it over to you. Thank you.
Thanks very much for your introduction. Yeah, so let's share my screen and start this this webinar. Here it is. Okay, so yeah, today we have a rather broad topic, and I would like to make it as an introduction to recall the most important things related to simulation, dedicated to thermal management and fire protection of buildings. So for that, I will have an introduction for modeling heat transfer application, and I would like then to show really how to build a model. So we will have a live demo where I will build a simple benchmark model, but even if it's simple, it contains all the ingredients for any kind of model you can think about. The ambient thermal property are yeah, quite interesting and important for buildings model. So I will take also time to discuss about this point, and then we will go through a number of simulation cases that cover thermal performance and fire protections. All these cases are documented, so you will be able to access this document afterwards, and they are, most of them are based on standards, so they are well documented and known cases. Okay, so introduction to modeling for heat transfer application. So first of all, what are the benefits of numerical simulation, and what can you expect from it? There are actually multiple motivations to use numerical simulation. The benefits are not the same for all projects. It depends on what you know already and what you want to know. I often say that the art of simulation is to tell to the software you are using what you know, so that you can get as much as possible from the software, from the simulation, to know more about the system you are interested in. So, for example, if you observe something like a poor thermal performance that are not expected, then the numerical simulation can help to understand how it occurs. So it helps, for example, if your model contains the temperature, thanks to simulation, it's possible to check the temperature at any point, at any time, which is of course very difficult in reality, but also it helps to check the importance of the different physical mechanism, like condensation, ventilation, or thermal bridge. You can see what happens if you switch on one effect. You can check the magnitude of each effect, while in reality you cannot, let's say, switch off the sun to see what happens when there is no sun. So you can really play with physical ingredients that lead to the reality. And if you are able to understand the physical mechanism, and if you know also the material properties, then it's possible to predict with a good accuracy the behavior of the device without building a prototype or without setting up an experiment. And if this done, and when you are able to predict with accuracy the behavior of system, then it's possible to explore new design. It's possible to invent new concepts, and when you find something that is really interesting, you have chosen a new design, then it's possible to optimize it. So you can optimize it manually by checking different configuration, different parameters, but you may know that there are also a number of algorithms that can optimize the system for you. You just input what can be modified and what are the objective of your optimization, and then a computer can suggest a different set of parameters that optimize your goal. But what is very important to keep in mind, and that's really my point for this introduction, is that all the numerical simulation are based on a model. So which means that we really need to clarify what a model is. And a model is a representation of a reality. That's this concept of representation is really important, and it's supposed to reproduce or to predict a real behavior, but for a range of configuration, and it's based on the law of science that describe physical phenomena and translate them in terms of differential equations. For example, Navier-Stokes equation describe fluid flow behavior, or Maxwell equation describe electromagnetic fields. And traditionally, the physics are segregated into a single physics category, like fluid flow, heat transfer, structural mechanics, etc. But in nature, they exist all together and they interact. So if you want to be accurate, it's needed to combine the physics in a model and get a correct description of a reality. So the reality, in a sense, is always multiphysics. And I insist on that already, but it's really important to keep in mind that a model is a representation of a reality. It's not the reality. And it's always simplified in a way or another, so that the model is manageable. The best model, I would say, is the simplest model that matches your need. So it will always rely on some hypothesis that will limit the validity of a model to a range of configuration, which is supposed to be the range of configuration you are interested in. And yeah, let's say the example of a geometry. If you draw geometry for a model, you are not going to represent all the teeny details of a geometry. You just keep what makes sense to explain what you are looking after. So if you are looking for the thermal performance of a building, then it wouldn't make sense to to describe something like the sand grains that are contained in the concrete. You are working at different scale, and that's perfectly fine. And if you decide to work on different topic, and for example a sub-millimeter scale, then you have to change this kind of hypothesis and take another accuracy detail in your geometry. That's quite obvious, but again, it's important to keep in mind that when you build a model, it's for a range of configuration, and the validity of your model is limited to this range of configuration, which is fine. So on this slide, I'm summarizing a classical process to go from a model to numerical results. So we start from the law of science, and the model description that make it possible to build a mathematical model. So this mathematical model consists in a coupled system of differential equation. And these equations are usually very difficult to solve exactly, but we discretize them usually using a mesh, and we gain a different set of equation, which is an algebraic system. And for this kind of system, we have a lot of efficient algorithm that can be solved efficiently on computers. And thanks to the computers, then we get a solution that is the best approximation up to tolerance that can be obtained for the discretization, so for the mesh that we have chosen. And in general, when you refine the discretization, when you use a finer mesh, then the computational cost increases, but also the accuracy is getting better and better. So that's the classical step for setting up and solving a model. So first of all, very important, the model definition. That's very first step, and you cannot go forward until this has been completed. So you need to define what you want to represent, the physics you want to account for, the material properties, etc. Everything that will be describing the model. And maybe while you are working on this step, you will realize that you miss some inputs, like you miss material properties. So you need to find them before you go to the simulation software. And then, yeah, you start using the simulation software, and rather straightforward, I would say. You define the geometry. So I mentioned that earlier. The geometry should be accurate up to a level of details that you want to account for, but also you will have to prescribe some boundary condition. So it's important to have a geometry so that you are able to prescribe a boundary condition. Let's say that you have a heat source in a device close to this heat source. The temperature field is changing a lot, and it's difficult to predict the temperature without simulation. So typically you cannot set a boundary condition very close to the heat source. But if you take something very far from this heat source, then you can assume that you have ambient temperature condition. So then you are able to prescribe a boundary condition. So when you build the geometry, you think about that, and you define geometry so that you will be able to define the boundary conditions. Then for all parts of the geometry, you have to define the material properties. They are, of course, extremely important to get accurate results. You cannot get any accuracy if you are not aware about the behavior of the materials that you are using. The physics, so for the different physics that are included in the model, you need to define the boundary condition, the domain condition, like sources, forces, etc. And then the physical description of the model is done, and you switch to the numerical part, so with a discretization based on the mesh. So the finer mesh, you define the more accurate the result, but also the most expensive. So the ideal mesh will be a perfect balance between a fine mesh where you need great accuracy because the physics field are changing a lot, and in region where the solution is almost constant, you don't need a fine mesh. Yeah, most of the time you can rely on automatic meshes that are deduced from the physics, but sometimes you may want to tune them manually to get more accuracy in one part or another. That's the same for the solver. You can rely on the default solver settings that are deduced from the physics and the mesh that you are using, but you can also optimize them manually if you want to get more performance or try something different. And then you are ready to solve. So depending on the size of the model, it's quick or slow, and then you get the result, and the post-processing step is where you really gain what you are looking for. So you can get some graphs, you can get maximum values, average values, etc. And yeah, as I mentioned, that's typically what you do for all the simulations. So before we build the example, I will give some explanation about what we do, especially for heat transfer. That's my part, and that will be the core of most of examples. So heat transfer occurs following three means: by conduction, convection, or radiation. If you are able to describe the three kind of heat transfer, then you are covering all heat transfer. So heat transfer by conduction is something that occurs on material. It's if you are in vacuum, you have no heat transfer by conduction. But as soon as you have a material, you get conduction. It requires a temperature difference, and the magnitude of a conduction is proportional to the material property, which is the thermal conductivity. So again, we have the physical laws that define the heat flux by conduction as minus the thermal conductivity times the gradient of the temperature. And this is something, of course, that you don't need to know, but that will be used under the hood to define the equation I mentioned in the introduction. So if you assume a case that we will demonstrate later on, where you have a wall made of insulation material with a cold surface, the blue surface here, and this is another view of the same geometry, but on the other side where you have a hot surface, then because you have a material between this cold and hot surface, so you have a temperature difference and a given thermal conductivity, then you will have some heat transfer by conduction. And here you have two different materials, so you will have different conduction effects depending on the material properties. We'll go back on this example rather soon. So the other mean of heat transfer is heat transfer by convection. This one also occurs only when you have a material and motion. You can have a forced convection when you have an active system responsible for the flow, or you can also have a natural convection. In this case, it's just the buoyancy and the difference of density that is responsible for the motion. That's what is illustrated here on the right. You have a cold surface here, you have a hot surface, and you have air in between, and you know that hot air is going up and cold air is going down, so you get this recirculation. And the color here that represents the temperature doesn't show a horizontal gradient as you would get with pure conduction, but something quite different, modified by the convection. And again, yeah, the physics law give a definition of magnitude of the heat transfer by convection, which is proportional to a material property called the heat capacity, Cp, and also the density. So we have the density times the heat capacity times the velocity times the temperature that gives the magnitude of a convection, heat transfer by convection, and that explains why the conduction is not defining alone the temperature profile in this example. And finally, we have heat transfer by radiation. I'm just mentioning here surface-to-surface radiation. We have also radiation participating media that's also a similar electromagnetic waves behavior, but yeah, let's focus on surface-to-surface radiation. So it occurs as soon as you have a transparent media between two opaque surface. So most of the time the transparent media is air, but it can be vacuum, it can be something else. And here the magnitude of heat flux by radiation is proportional to the surface emissivity constant, and the temperature, the difference at the temperature of each surface at the power of 4. So you can see that when the temperature are getting large, this quantity can be very large. So in this case, the heat transfer by radiation may be very large. And when you want to account for heat transfer, by default, you have to combine the three modes of heat transfer. And if you know that for one reason or another, for example, there is no transparent media in your geometry, or there is no motion, then you can skip one of them. But if you don't know, then you may include all of them. Okay, so now I will show this example, this benchmark example, and we will build the model together. So first of all, I have to describe it. So this example, so if we recall here all the step, model definition, geometry, etc., we have to start with the model definition. But in this case, we are lucky because the model is well documented and defined in European standard for thermal bridge in building construction, so heat flow and surface temperature. So this benchmark, this norm from 2007, so it's the ISO 10211, gives all the details, so the geometry, material property, the physics, so all the physical details needed to build this example, and then it's up to us to find a mesh and a solver settings that match the accuracy they expect. Okay, so the geometry for this thermal bridge is the geometry we have seen before. It's a piece of wall which is 1 meter by 1 meter and a thickness of 20 centimeter. So this is an insulating material, and it contains iron beam. So as you can expect, it will be responsible for bad thermal bridge, and this beam is 10 centimeter thick, 60 centimeter long, and 50 millimeter of high. So that's pretty simple geometry. In general, the geometry is of course much more complex, and you can either draw it in simulation software or build it in a modeling geometry, a CAD software, and then import it in the simulation software. There are a number of standard tool for that and bridges between simulation software and CAD softwares. Then for the material properties, we have a material property for the insulator and for the iron, so it's only two materials, and that's it. For the physics, of course, we have a thermal conduction in solids. I said that as soon as you have a material, you have conduction. There is no motion, so there is no convection, and the radiation is assumed to be small enough to be neglected. So this model will contain only conduction. And on both sides of this geometry, so the blue face here represents the exterior and it's cold, and the inner surface here represents the interior, which is hot. We don't have a prescribed temperature, but we have a convective heat flux condition on both sides, so which means that we have an exchange heat flux which is proportional to the temperature difference between the surface temperature and the exterior or interior temperature times a coefficient, which is the heat transfer coefficient, the convection coefficient here, and that's it. For the mesh, so this is up to you. This is not something defined in the standard, so we have to find the good one, but we expect that we'll have temperature gradient at the junction between the iron bar and the insulation material. So we will use a finer mesh for the bar here. For the solver, there is nothing special to it. It's such a small model that we can just use the default and it's very quick to get a solution. And then, of course, the post-processing is what we are really interested in. So we expect to be able to plot the temperature everywhere in the geometry. And again, the standard gives some target value for the highest temperature on the external side. So on this side, because of the iron bar, you expect that, yeah, you will get some heat from the inside that is reaching the external side. So the maximum temperature will be computed, and also the heat flux. So due to a thermal bridge, the heat flux on this face will be larger, but without iron bar for sure. So let's switch to COMSOL Multiphysics to build this model live and to see how to proceed. So we have this model wizard that will guide us to build the model. So first question is to select the space dimension. So obviously it's a 3D model. Then we have access to a number of physics interface. You can see all the physics here. We are starting with a single physics model with heat transfer in solids. We could add more, but I start with just one physics. And then we can also study different kind of studies, stationary, time-dependent, or more advanced studies. And in this case, the benchmark is looking at the steady state, not the startup effect or things like that, but just the steady state with a stationary study. So we are done for the wizard, and now we are already starting to define the details of the model. So we find again the same step as I mentioned before, the geometry, the material, the physics, the mesh, and the solvers, and the post-processing will come in the results. So for the geometry, we don't need to import this geometry from another software. We can easily build it using the tools that are available. Like we need a block for the wall. So the block is 1 meter, then it's 0.2 meter thick and 1 meter high. So we can check how it looks like. This is this block. We will add another block for iron bar. So this is 10 centimeter, and then it's 60 centimeter long and 50 millimeters. So you can see here that we have a unit, and if you don't want to work in meter, you can specify the unit using brackets like that. So here I say I want 50 millimeters. And yeah, I have to think a little bit about the position. I will define the position of the center of this bar in the middle of this block, so 0.5 and 0.5, and the middle of the bar will be located at 0.3 for y coordinate. So if I build everything, I can see that I have my bar made of iron, and the insulating material here. As you can see, they intersect, so there is a region where, in a sense, we have both material, and this is something that is detected at this step. And if I switch to wireframe rendering, you can see that there are 3 domains, one here, another one here, and another one here. So I don't want 2 domains for the iron bar, it's only one in reality. So I will perform an additional step here for my geometry. There is something called virtual operation to form composite domains. And I will say that these 2 domains are actually a single domain. And if I build all, now I can check that I have 1 domain for the insulating material and 1 domain for the iron bar. So typically I'm done with the geometry definition, and I can switch to the material definition. So for the material here, I could browse material libraries and get predefined materials, but in this case, I really want to stick to the standard. So I will create a blank material and define the material properties myself. So for example, for this insulating material, or for the wall, the thermal conductivity has to be equal to 0.1, and I can also specify density, even if I'm not going to use it for stationary study, but just for completeness, I define everything. And if I add another material here for the iron bar, so the thermal conductivity is much higher, it's about 50. And the density as well is higher, and the heat capacity is a little bit less, like that. So now I have 2 materials. I have this one defined on domain 1. Domain 2 is overridden by the next material, which is iron. Okay, so this step about material properties is now completed as well. I can switch to the physics. So I have heat transfer in solids. So this physics interface is responsible for translating the law of physics into equations that the mesh and the solver will take care of afterwards. So for example, in the solids, there is an equation that we rely on with Fourier law, for example, which is recalled here. And you can see that they involve some material properties, and these material properties are said to be taken from material. So we define the material properties, and now these material properties are used to generate the equation that we want to solve. We see that so the solids equation are used everywhere, which is fine. By default, there is a initial value, which is a kind of guess for stationary studies. So we don't really the solver will change this value to get the converged solution. And we have a default boundary condition, which is the thermal insulation condition that we want to modify, because we don't want thermal insulation everywhere, just on this boundary here and on the top, below and behind, but not on the sides. So I will go in the physics here, and for the boundary select another kind of boundary. So there is a heat flux boundary condition here. I have to select the boundary where I want to apply, so I can change the view, for example, this one, and thanks to this tool, I can select all the boundaries and go back to the view. Okay, I took all the boundary except this one, so now I have all the interior boundaries. So I'm saying that I want to apply this boundary condition to all this boundary, and this boundary condition is a convective heat flux condition. So here you can recognize the condition that I showed before, where the heat transfer coefficient is given and is 10, and the exterior temperature, the benchmark uses a normalized temperature difference, so 1 degree between the inside and the outside. So here I'm just setting 1 Celsius, even if it's rather cold for inside. That's the standard, and that's the definition of a model we want to reproduce. And I need to use another heat flux condition for the exterior. So the same convective heat flux condition, the same heat transfer coefficient, 10, but different temperature. So 0 Celsius here. And of course, I need to specify which boundary are exposed to this condition. So these 2 boundaries. And that's it. And I'm done with physics. So if we go back to thermal insulation, you can see that it has been overridden in most of the boundary, but it's only now active on 4 boundaries, which is exactly what I was willing to do. So now we can check the default mesh. The default mesh is like that. It's pretty coarse for the iron bar, for example. So we can easily tune it manually. We can edit the automatic sequence, and we see that there are some instructions to build the mesh, and we can here prescribe a different size for the bar here. So for one particular domain, this domain, we'll say that we want a much finer mesh, and rebuild the mesh, and you can see that now we get a finer mesh here, and it will help to get accurate results. For the solver, there is not much to do. We can just solve. It's very quick. Okay, so there is a progress, but we hardly have time to see what's happening, and we get a plot by default that shows the temperature. The temperature is given in Kelvin, so we specified everything in Celsius before, so we'd better switch the graph to Celsius as well. So we see that we don't get exactly 1 Celsius inside and 0 outside because it's a heat flux condition, it's not a temperature condition, so that's perfectly fine. But the big thing is that we see the effect of a thermal bridge quite obviously with this high temperature on this side, that is supposed to be a cold side, but due to the thermal conductivity of iron, it's not so cold. And then the benchmark gives some indication about what we should find for the maximum temperature on this side, so we can evaluate the maximum temperature on the surface. So the surface formed by these 2 boundaries here, and we can check the maximum temperature on these 2 boundaries in Celsius. And so if we ask to evaluate, we see that the maximum temperature is 0.8 Celsius. And if we want to see how much heat flux we have for 1 Celsius or 1 Kelvin, but the same of difference between the 2 sides, we can also integrate on the surface the inward heat flux. So here there are a number of predefined variables. You don't need to know them. You just type what you are looking for, and here you see that there is a boundary flux which is called inward heat flux, and you select it. That's the name of the variable, and you can integrate it on the boundary, and you see that you lose about half a watt on this surface. So we get the simulation outputs piece, and I mentioned that when you have a model and it's working well, then you can modify your design to see the different heat losses or different maximum temperature for different configurations. So let's assume, for example, that everything is made of insulating material. So it's very simple. You just deactivate these material properties, and you get for all domains you get the insulating material properties, and then you just have to rerun the simulation, and you can check what is the difference, and you can obviously see that the temperature profile is very different, and you can then reevaluate the maximum temperature and see that now it's much smaller on the outside, which is expected because you no longer have thermal bridge. And you can also check what is the effect on the heat flux. So you see that something like 20% of a heat flux is saved without the thermal bridge. And you can explore many configuration. I will not check everything, but let's imagine that you want to change the position of an iron bar so that it's not going through all the thickness of a wall, but just half of it. You change the position of the center here. You rebuild the geometry, and now if we change the view, we see that it's not going through all of it. And if we go back here, so we have a wall, we reactivate, we re-enable this this condition here. So we have iron bar and we have a wall here. So now you see that there is no imprint of iron bar on the external side. If we quickly check the physics settings, we have a heat flux as before on these sides. We have another heat flux on the exterior side, which is fine. We get a new mesh, of course, because we have a different geometry, and we can solve it. And hopefully we get a solution there. And on the solution, we get a small sign that there is a thermal bridge, but clearly not as large as before. So we can check clearly the value of the temperature. So, oh yes, I'm selecting two boundaries here, this one and this one that is now in the middle of the geometry. So I clearly don't want to compute the maximum on the internal boundary, but just on the external boundary to compare things that are the same. So let's evaluate again. Yes, and you see that the maximum temperature is not as small as in the case without thermal bridge, but much smaller than in the first example. And if we check the heat flux through this wall, then we see that it's also much smaller than in the first case, but not as good as in the last case. So that's a quick illustration of what you can expect from simulation. Okay, now back to the presentation and the slides and a word about ambient thermal properties. So ambient thermal properties, the motivation for that is to get realistic condition for outdoor applications. Depending on the place where you are, depending on the time, the date, etc., you have different conditions, and it's useful to know them. You are also often interested in extreme conditions. Is the design good for the hottest or the coldest temperature condition? And also to customize a model. You may develop a model for one particular client, and then you have a particular customer, and you want to use the same kind of model but for another customer in another location. So then you need to update your ambient thermal property to match the reality. And most of the time the ambient property are obtained from weather stations that monitor let's say the temperature for every hour during years and years, and for particular date or month or week in the year, you will gather that data. Like every curve here will represent for a particular month the number of times for each hour where you have noticed that the temperature was 3 Celsius, 4 Celsius, 5 Celsius, and so on. So you have this large amount of data, and if you process this data, you can, for example, deduce what is the average of a typical temperature for every hour in a day, and you get these kind of curves here. And you can also get more than the average temperature. You can get the maximum temperature that has ever been recorded, the minimum temperature that ever been recording, as well as the standard deviation to get a typical hot temperature, or if you take 2 times the standard deviation, then you get a very hot typical temperature or cold temperature. So you can, from that, you can generate any kind of typical weather condition to use in your model. And the good thing is that these kind of data are quite easily available. For example, Ashfry is compiling this data for something like more than 8,000 of stations around the world, and you can reuse them to define ambient conditions. These data, as I mentioned, are depends on the seasons, on the months, on the time. So you can really use that as a transient condition in your models, and that make it possible to account for day and night temperature, for example. And here we see the temperature variation during more than 10 days for a particular location and particular date. And of course, you should decide if you want the typical temperature, maximum, extreme conditions, and so on. And once you have defined a profile for your ambient condition, you can include that in your model. For example, if you prescribe a temperature condition or heat flux condition, then you can refer to this database through any tool and then get the effect of this ambient condition on your model. And if you change the weather station, for example, in your model, then you get the behavior for another place. Okay, so now I will go through a number of simulation example related to our applications. So again, I'm taking very classical example from standard. So this one is from a European standard about action on structure exposed to fire. So when we are looking at fire protection, there are some passive protection capabilities that consist in making a building good to resist to fire for a time that is long enough so that you can evacuate and it's not being destroyed too quickly. And one way to make sure that material of a building will not be destroyed is to make sure that they are not getting hot too quickly when they are exposed to fire. So this benchmark is about monitoring the temperature in the center of a block that is exposed to fire. And what is very interesting in this benchmark to me is that everyone can easily understand that modeling fire in all details is something very difficult. But here they give a key information to model fire in an efficient way, and then it's possible to build a model quite easily, but it's still of interest for the model. Actually, they define the benchmark case for this standard. So they define the exposure to fire on a solid using two boundary conditions. One for convective heat flux, where the external temperature is the flame temperature, so 1000 degree in this case. And there is also, because the temperature is high, then the radiation cannot be neglected, and then the model combines convection and radiation on the external surfaces that are facing the flame. And you have these two conditions. And another thing that is important is that because the temperature is changing a lot between the beginning of a simulation and the end of a simulation, then the material properties are modified, and they also provide the material properties as a function of the temperature. So here it's in Celsius. From 0 to 1000 Celsius, you can see that the thermal conductivity is decreasing. And this is something that induces a nonlinearity in the equation, and we want to model. So this model so monitor the temperature in the center of the geometry. So at the beginning we have a cold temperature, and we can see that it increases. Maybe you can distinguish a blue and a green curve that are the simulation curve and the reference curve, so they are extremely close, which is a good thing. And we get the temperature profile for 3 hours here. And we can also represent the temperature in the block as a function of the time in this animation. So you can see that the bulk of the block has this dark red color that represents low temperature, and the edge of the block have the light yellow, which represents the high temperature. And we'll see how the hot temperature propagates in the block during the time. So of course it's heating more and more. Again, this kind of simulation is to make sure that it takes long enough for the material to get above a certain temperature so that it resists to fire. Yes, and in my introduction, I mentioned that in general models are multiphysics, and now we're getting back to that, because when you want to work on fire protection and to design the material size and property to resist to fire for a time that is long enough, you have to think about the structural mechanics aspect of a problem, because the material property from structural point of view are not the same at cold and hot temperature, and you have also thermal expansion due to temperature change. So this is something that is covered in these new examples, going from the same standard action of structure exposed to fire, and they cover a number of points. They cover the fact that the material property from structural mechanics point of view are non-linear. So it means that for large deformation, you have a non-linear behavior of the material, and these material property are temperature dependent. And so this is about computing the thermally induced stress in a beam that is blocked on the two ends and that is exposed to two different temperatures on the upside and the outside. Again, the material property are given by the standard, so the thermal elongation is not a straight curve, but it's something that is temperature dependent. So here you get the elongation as a function of the temperature, and you can see that at some temperature you get some change in the slope. And the relation between the strain and the stress is also given in this benchmark, and we can see that for low temperature there is a rather linear behavior and then a sharp change when you get too high stress, while for larger temperature then the material is softer and the deformation is smoother on this region. So this benchmark defined two cases of interest. One, you are just heating from 20 Celsius to 120 Celsius, and you expect thermal expansion just due to heating, and you have to compute some stress in the geometry. And the second case is where you have heating and you have also a temperature gradient between the upside and the downside. The upside is very hot and the downside is at the ambient temperature. So in this case, you expect very large thermal stress in the geometry, and that's something you want to study. And this kind of multiphysics problem, that's something that can be covered by simulation. And still about buildings and multiphysics, but a completely different topic, more related to thermal performance, is when you want to study the thermal loss through a wall and also the humidity. You get you get a heat flux between the exterior, which is at cold temperature, and the interior, which is at a high temperature. And due to the heat flux, okay, I have some noise behind me. I hope it's okay to hear me. If not, just let me know. So the exterior conditions are defined here. So cold temperature of 0 Celsius and relative humidity of 80%. And inside there is interior temperature of 19 Celsius and relative humidity of 50%. So the structure of a wall is described here. We have a OSB panel on the top here, which is facing the exterior. We have some wood for the structure, and we have a cellulose material inside, and of course some plaster for outside. And this model study the difference of behavior with or without a vapor barrier. So first of all, we have to define what is the physics we want to solve for, and luckily this is something that is defined by a standard. In this case, we are taking the equation they are described in the standard EN 15026 from 2007, and they give the temperature equation and the equation for relative humidity. And as you can see, for example, in the temperature equation, the heat flux contains the Fourier contribution, but also contribution coming from the relative humidity. And that's the coupling is also on the other side. So in the equation for the relative humidity, the saturation pressure, for example, is a function of the temperature. So these equations are again documented and predefined. So the only things you have to do, which is not a small thing, is to define the material properties that are entering in this equation. All the material properties for this humidity problem are usually a function of relative humidity. And here I'm showing the kind of material property that are used in this model for the wood, for example, but you need the same for all materials. And from that, you can compute the temperature profile and the relative humidity profile for different times and external and interior conditions. In this model, what is particularly interesting is to check the maximum relative humidity to see if there is a condensation risk. And typically in this case, if you compare the result with or without vapor barrier, you get a large difference in the results. Okay, so that's all the example I was willing to show today. I like to wrap up. So today I try to cover the different benefits for numerical simulation, but also the limitation. What is a model? Where it's coming from the law of science, what it's going to the numerical algorithm and to get an approximate solution. So it's always based on some hypothesis. When you want to describe the reality, you often have to combine different physics, and for buildings, we are very often interested in heat transfer, moisture transfer, as well as structural mechanics. And if you want to continue looking at simulation after this webinar, I warmly invite you to go on COMSOL.com website, and especially on COMSOL.com/model, you will find all the model I have presented today. So this model are available, documentation of this model is available for download. And if you are interested in doing simulation yourself, then you can request a software demo on our website as well, and request a trial version. Okay, maybe we have some questions that I haven't covered during my presentation.
Yeah, great. Thanks, Nicholas. Yeah, I think we do have some questions, and we definitely have some more time for questions here. And right before we get to those, just wanted to go over this real quick here. But wanted to again thank all of you for joining us. Thank all of our members, our board of directors, our volunteers, and a huge thanks to our top tier sponsor, Shrinergy, for on the go and in your house or office microgrid solar powered battery solutions for not if but when the grid goes down. Mitsubishi all electric systems for getting to net zero in new and existing buildings, multifamily, single family, you name it. Heat pump systems that work down to -13. And T-Stud, structurally insulated framing systems to save money behind the walls during your new construction project. So yeah, I do see some questions here. One of them I wonder about energy modeling, and I was wondering if you know, this kind of system or tool ties into like your ASHRAE 90.1 is the one I can think of as the big, obviously popular one for buildings. But does this have the ability to tie into those kinds of systems and help produce those, you know, either those code compliant or green building energy models?
Yeah. I would say that the point is that there are a number of classical configuration where we already know what to do, and I would say the professional experience is enough to to find the good designs. But as soon as things get larger, bigger, um, or, or unknown, then the intuition or of experience is just not enough. So yeah, in this case, if you really want to get good quantity, good accuracy on your prediction, then yeah, the simulation is of interest.
Great, thanks. The other question is, I would like to know if the moisture transport simulations can take into account moisture movement by airflow.
Okay, so that's a good question. In the example I've shown and the reference I gave for this standard, which is about moisture transfer in building materials, the moisture flow is not explicitly taken into account. So what I mean here that there are some moisture motion due to capillarity, but they are accounted in an implicit way, I would say. And if you want to account for moisture flow due to air movement, for example, you need to use another set of equations. So in COMSOL Multiphysics, we do have different what we call domain properties for domain where you want to compute the flow velocity explicitly, and domain where you want to use the simple building material models. So depending on the cost you are ready to pay for your simulation in terms of hours or memory, you can use one approach or one other, but both are available.
So just again, that answer is, yeah, it's just another piece on the tool. Is that correct?
Yes, exactly.
Okay. Is there a combustion model so that you can combine this with a structural model?
Okay, so when we talk about combustion model, what on my side I have in mind is related to chemical reactions and exothermic chemical reactions. So which is something that is covered by COMSOL Multiphysics, but yeah, quite far from what we have seen today. But so you can very well define chemical species and reaction, exothermic reaction, and to get a combustion model. These models are usually very heavy to solve for. Now, if it's just to get the interaction between a surface exposed to flame and the structural deformation, that's more related to the example I showed for the beam. So this, yeah, in this case, we are not really modeling the combustion. We are just modeling the effect of a combustion on the temperature conditions on boundaries, and this is something which is really lighter to define and to solve for.
And on that same note, can it couple with other modeling tools like, for example, they used fire dynamic simulation?
I'm sorry, I didn't get the question. Could you repeat it, please?
So they were just, as a follow-up, they were saying, can it couple with other modeling tools maybe? And they were using an example such as the fire dynamics simulator.
Okay, so I would consider two kind of couplings. One is if you have another tool that give you, for example, a temperature or heat flux profile due to combustion, and you want to use this profile to set a boundary condition, then that's the simplest case. If you are able to export this data to a text file or to an Excel file or yeah, any standard data, then you can import this as a boundary condition in COMSOL Multiphysics. So that's straightforward. What is more tricky, if you want to solve for COMSOL during a number of time steps, then to send COMSOL solution to the external software and to iterate like that. That's not impossible, but you need to use some programming tools that we have a programming API that is available, so that you can call COMSOL functionality without using the user interface, but just through a program. And we have a number of examples of coupling between two different software. One is COMSOL and one is another one.
Great. So the next question, and I'm going to spell this word out here, is how about Pyrolys? I think that's Pyrollysis model. How about that? How can that simulate the phenomena when a wood is exposed to fire?
Mm-hmm. Yeah. So clearly yes, and this kind of model is a perfect illustration of what I try to describe when it comes to model. It really depends on what output are you interested in. Are you interested in just how the wood will behave from a thermal point of view during the combustion, or do you want to know a lot about the chemical composition of it? So depending on that, you can use a simple model to describe the change of material properties as a function of the temperature or as a function of the damage. We have a predefined feature, for example, for what we call irreversible thermal transformation. So that's typically what happens when you have a combustion. Your material will change due to the effect of a temperature and is burnt or destroyed in some way. So get different physical behavior. So that's, I would say, the simple approach. And if you want to go more again in the chemical composition and follow the different reactions, that will be again exothermic reactions, and you will have leaks due to evaporation. That's also possible, but that has clearly has a different cost and require more expertise also from the user. For all these questions that are quite specific and related to one application, I can suggest to go on our website for the models, and we have also archived from our user conference. So we have hundreds or thousands of papers that have been published by our user that show how they tackle this problem or this problem. So if you have any keyword in mind, like wood combustion or something like that, you can try that on our website and to see what have been published on the subject.
Great. Well, yeah, thanks for bringing that up. I had a question. I did see something about electromagnetic frequencies mentioned as you were going through the simulation. So I have to ask, I do know that there is concern in the green building movement on reducing or avoiding exposure to EMFs. So I wanted to see if this is simulating walls that are helping protect against that, or if that was just something else that I caught wind of that's not connected.
No, but that's a very good observation. In electromagnetics, there is one field about electromagnetic compatibility that says how much a device radiates and how you can protect the surrounding or the exterior from the electromagnetic effects, and that's typically something that you get from the electromagnetic simulations. So yeah, we do have an application of where we look at the magnitude of electromagnetic fields induced by some lines or device can be from the mathematical point of view, whether it's for electronic box or a car or a building, it doesn't change much to the equation we are solving. So yeah, you can really do that. Maybe the one limit is when it comes to waves physics like acoustics, electromagnetics, to capture the variation of the field. You have to use a mesh, and the mesh size is given by the wavelengths of the physics you're interested in. So if you are looking at short wavelengths in a very large scale like buildings, then it could be prohibitively expensive to compute. But that would be the limit.
Absolutely, sure. And another question is, does this tool come with, you know, if you're putting together a model, does it come with recommendations on what to do to make improvements, or is that something you would need to know going into this?
Okay, so, I understand you are talking about your own model, but if I'm going to start with the models I presented. All the models I presented are coming with a PDF documentation that explain what is contained in the model, what are the equations, what are the material properties, the geometry, so all the description of the model and also all the results. And it's followed by a step-by-step instruction. If you want to rebuild exactly the same model, you just have to follow the step-by-step instruction. And these step-by-step instructions are coming with suggestions or advices. Say we are doing this to improve this part of this part. So if you reproduce a couple of examples in your field, you will learn a lot already. We have a lot of users that just learn by reproducing a couple of good examples, and then they manage by themselves. Otherwise, when you solve the model, there is no wizard that will tell you try this or try this. If you really have a question about, you know, you have something you want to change your model or you want to optimize, then my recommendation would be to reach the support. We have many people working to help through the support, and they will guide you to reach your goal.
All right, great, Nicholas. Well, I appreciate your time and COMSOL's time on this. Thanks for putting this on. And real quick before we wrap up, again, can you just reiterate, if people have more questions or want to learn more, where can they go?
Okay, sorry, you mean if people have more questions, if they want to reach us, obviously the best is to reach us through our website. You will get all the contact information, and yeah, you can contact us for modeling projects, to try the software, or just to access the model documentation directly on our website.
All right. Well, thank you very much. Thank you all for joining us. Take care and have a great rest of your week. Thank you.